All right, so we pass by Mars. We're going to assume that Earth, Mercury, and Venus are on the other side of the sun. We're going to be looking at the sun. This is what the sun looks like during an eclipse. The moon is moving in front of the sun. This is a total solar eclipse. You've seen during the day, sometimes you can see the moon. Well, what if the moon got right in front of the sun? That's what happens. You move into the shadow of the moon, so it moves across the Earth's surface, and you see this type of feature. The sun goes dark in the middle of the day. It looks like it's midnight, but it's not. It's 1:30 in the afternoon, and the stars come out. This is what it looks like from space. So the people living on this part of the Earth are in a solar eclipse, right? Because they're inside the shadow of the moon. And so if you're on the edge, this would be maybe total eclipse. This would be maybe 30%, 20%, 10%, depending on where you are. In Dallas, we had like a 40% solar eclipse. And it was pretty fascinating. I was working out in my yard, and it began to get shadier and cooler, and I thought that a cloud had moved in front of the sun. And I looked up, and there were no clouds. I thought, that's weird. It feels like it's getting shadier and cloudier, but there's no clouds, and I forgot. It's the eclipse. I actually detected the eclipse. So I went to my garage, I got out my telescope, turned it toward the sun, and I didn't look at it because you'd go blind. But I turned my telescope, I had a reflection telescope, turned it toward the sun and projected the image through the eyepiece on the wall of my garage, and there was a solar disk with a big chunk, like the Cookie Monster taking a big bite out of it. It was a partial eclipse. This just shows the progression of the shadow across the Earth. So people that are in that line, they're going to experience a total solar eclipse. Right, this is the terminus. That's morning. That's morning. We're in daylight now, and these people are experiencing the total solar eclipse. And so that's how they can tell when they're going to occur. And they can even take these types of projections and record back through time and determine when there were total solar eclipses in the past. That's one of the ways that they've been able to anchor the dates of the Bible. Because in the eponym list in Assyria, they actually mention total solar eclipses when the sun goes black. And so they can run these progressions backwards and tell exactly when those total solar eclipses occurred, and they can put dates on the eponym list. Those eponym lists mention biblical kings, so they can put dates on the biblical kings. So it's an important event. Whenever there's a total solar eclipse, the moon is in front of the sun, and so you can actually see the atmosphere of the sun, called the corona, that radiates around it. There's a superheated gaseous envelope around the sun called the corona. It's its atmosphere, and you can see it during a total solar eclipse. And it is somewhat of a coincidence, or God's plan, that even though the moon is much smaller than the sun, the moon is just at the right distance from the Earth, that the apparent diameter of the moon matches the apparent diameter of the sun perfectly when they overlap. And that allows the corona to be seen. Not only the corona, but you can see solar flares. But yeah, the Earth exists along this equatorial region, which is very nice because that keeps us nice and toasty warm. If you tilted that equatorial region just slightly, we would all become popsicles very quickly. This is a photograph of the shade under a tree taken during a partial eclipse, probably about a 40-50%. But you see those arcuate shapes? That's the eclipsed sun. It's acting like a pinhole camera. The light coming through the leaves on the tree. And so when you look at it during a total or a partial eclipse, you can see something radically different because you're actually seeing the moon move in front of the sun. It's creating those little arcuate shapes. We've sent probes to the sun to actually photograph it. And what it is, a big ball of plasma. Whenever you superheat gas, it goes into what they call the fourth state of matter, which is like a liquid light. It's like a light that behaves like a liquid. It's called a plasma. Plasma is called the fourth state of matter. What are the three states of matter? Solid, liquid, and a gas. So at very low temperatures, you have solid, right? You heat it up, and it goes from a solid to a liquid. You heat it up further, it goes from a liquid to a gas. Well, what happens if you continue to heat it, like the sun? They've recognized that gas will actually begin to become luminous and flow. And that's what they call the fourth state of matter, superheated gas called plasma. You're familiar with plasma. If you've seen, or several places, if you've been to science shops, you'll see the plasma balls where they have some kind of inert gas inside at very low pressures, and they run electrical charge through it, and you can actually see the plasma forming. If you've ever been shocked, like you're reaching out toward a light switch, and that you see that blue bolt of electricity, that's not electricity. You can't see electricity. According to physicists, electricity or massless particles, a flow of massless particles, you can't perceive them. What you're perceiving is that flow of electrons actually superheats the air, and that superheated air glows like a liquid light, and that's plasma. Have you seen a lightning bolt across the sky? Plasma. Okay, superheated gas. So when you see a lightning bolt, you're not seeing electricity because you can't see electricity. You're seeing the superheated gas of the plasma that's forming around that electrical charge that's moving through the atmosphere. And that's what the sun is made of. It's made up of a superheated gas, liquid light that's sort of circulating around the surface. Well, the sun is like lightning. It's like a big ball of lightning. And you can see the influence of the magnetic field on the plasma. It's like storms. And where you have the most intense storms that can block out enough of the heat coming from the interior that it creates what they call sunspots. This is a sunspot. And they grow in time and change position. They're storms, but they're not storms in the atmosphere like a wind. They're a storm of magnetism. So if you have any metal, it'll fly around like it's in a wind, but it's not. It's just, well, it all melt. It all vaporize, but just, so what is this right here? It's a sunspot in the plasma. Close-up of sunspots. This would be a photograph of a sunspot on the surface. You can see the loops of flares coming out of it. So this would be sunspots, these storms across the surface of the plasma. And you can see they move through time, change positions.
The sunspots are the cold areas?
Well, yeah, I'm not sure we'd say cold, but less hot, because the heat that should be coming out there is being pushed to the side, so it creates a colder region. And since the heat or the light coming from it is reduced, it appears dark in images. Sunspots. And most of the solar flares that you see here, these jets of energy that come out along the perimeter of the sunspots where it's concentrated. Not all of them, but most of them are. But anyway, this is just photographs taken of the plasma surface of the sun at different times, so you can see how it changes its shape. Those are flares. You can see how it progresses.
Those come out of the middle of the sunspot if it's too big or something?
Not the middle. They come out of the edges because the heat that's coming from the core of the sun, it should come out on top of the sunspot. But because there's a magnetic storm there, it pushes it to the side. Well, as it pushes it to the side, it coincides with the heat coming from that region. So it compresses it, makes it more intense, so that's generally where you get the release. Anyway, you see the flares that are occurring around the edges of a sunspot? And the magnetic field's trapping the material in the flare and pulling it back to the surface. Here's some more loops. This is the size of the Earth, right here, that little ball. So this gives you an idea of how large the flare is.